formally welcome and introduce Professor Chang and Dr. Wang. Professor Chang received the BE Engineering Honours degree from National University of Singapore in 1989, and the Masters in Engineering and PhD degrees from Nanyang Technological University, Singapore in 1993 and 1998, respectively. He served as a technical consultant in industry prior to joining the School of Electrical and Electronic Engineering, NTU, in 1999, where he is currently an associate professor. He holds joint appointments with the university as assistant chair of alumni of the School of Electrical and Electronics Engineering from June 2008 to May 2014, deputy director of the Center for High Performance Embedded Systems from 2000 to 2011, and program director of the Center for Integrated Circuits and Systems from 2003 to 2009. He has co-edited 5 books, 13 book chapters, more than 100 international journal papers, of which around 80 are in IEEE journals, and more than 180 refereed international conference papers. He has been well recognized for his research contributions in hardware security and trustable computing, low power and fault-tolerant computing, residue number systems, and digital and image processing. He has delivered more than 50 keynotes, distinguished lectures, tutorials, and invited seminars, including tutorials at the 2021 IEEE International System on Chip Conference, Asia, and South Pacific Design Automation Conference, the 2017 and 2021 IEEE International Symposium on Circuits and Systems, and the Advanced CMOS Technology Winter School, 2020. Dr. Chang currently serves as the Senior Area Editor of IEEE Transactions on Information Forensic Security and Associate Editor of the IEEE Transactions on Circuits and Systems and IEEE Transactions on Very Large Scale Systems. He has also served in the past as the Associate Editor of the IEEE TIFS and IEEE Transactions on Computer-Aided Design of Integrated Circuits and Systems from 2017 to 2019, IEEE Access from 2013 to 2019, IEEE TCAS 1 from 2010 to 2013, Integration and the VLSI Journal from 2013 to 2015, Springer Hardware, a Journal of Hardware and System Security from 2016 and 2020, and Microelectronics Journal from 2014 to 2020. He is also guest edited 8 journal special issues, including IEEE TCAS 1, IEEE Transactions on Dependable and Secure Computing, IEEE TCAD and IEEE special issues, including IEEE TCAS and IEEE Journal on Emerging and Selected Topics in Circuits and Systems, of which 4 are related to hardware security. He has served key appointments in the organizing and technical program committees of more than 60 international conferences, mostly IEEE, including the General Co-Chair of 2018 IEEE Asia Pacific Conference on Circuits and Systems, and the inaugural workshop chair and steering committee. Am I audible? Hello?
Yes.
He has served key appointments in the organizing and technical program committees of more than 60 international conferences, mostly IEEE, including the General Co-Chair of 2018 IEEE Asia Pacific Conference on Circuits and Systems, and the inaugural workshop chair and steering committee of the ACM CCS Satellite Workshop in Attacks and Solutions in Hardware Security. He is a 2018-2019 IEEE CAS Distinguished Lecturer, a Fellow of the IEEE and IET and AAIA. Dr. C. Wang, the second speaker, received both the BE Engineering degree honors and PhD degree from the School of Electrical and Electronic Engineering, Nanyang Technological University, Singapore, in 2016 and 2021, respectively. She is currently working as a postdoctoral researcher in Professor Chip Hong Chang's research group. Her areas of research include hardware security, machine learning accelerator, machine learning security, and so on. She has published 6 IEEE journal and conference papers, including Journal on Emerging and Selected Topics in Circuits and Systems, International Symposium on Circuits and Systems, Asian Hardware-Oriented Security and Trust Symposium, and International Conference on Solid State and Integrated Circuit Technology. She ranked the first place and received the most popular poster video award in AI Research Student Conference, ARSC 2021 poster competition. She is an active member of IEEE Society. She has served as a reviewer for ISCAS Asian Host, International Symposium on Hardware-Oriented Security and Trust, Attacks and Solutions in Hardware Security, IEEE Transactions on Computer-Aided Design of Integrated Circuits and Systems, etc., since 2017. So welcome, Professor Chang and Dr. Wang. Over to you, Professor Chang.
Thanks for attending this tutorial on security of deep learning, a hardware perspective. My name is Chang, and I'll be the first speaker of this tutorial, followed by Dr. Wang, who is my research fellow. Both of us come from the School of Electrical and Electronic Engineering, Nanyang Technological University. The content of this tutorial comes from this IEEE JACCAS survey paper published in 2021. This is an open access paper. You are welcome to download and read this paper after our tutorial. This is the brief outline of our tutorial. First, I'll give an overview of deep learning deployment. Then I'll introduce some hardware platform for deep neural network implementation. I'll talk a little bit about the integrity threat, and due to the time constraint, I'll only briefly cover the mitigations of fault injection attack. In the second part of the tutorial, Dr. Wang will talk more about the confidentiality threat and mitigation. Deep learning models have been deployed on cloud computing platforms provided by different vendors such as Microsoft, Google, IBM, Amazon, Oracle, and Alibaba. In each endpoint application, it is often needed to process the data nearest to the source to ensure privacy, increase reliability, and minimize bandwidth. Hence, low latency and energy efficient hardware is required to support on-device inference without relying on network connectivity. Many deep learning implementation-friendly platforms and development boards have been made available to meet different application latency and energy requirements. These AI accelerators include NVIDIA Jackson Nano development boards, Raspberry Pi low-cost ARM embedded microprocessor, Intel VPU, Xilinx DPU, and Google Edge TPU. This figure provides an overview of AI deployment in an IoT ecosystem. Sensor data are fed to end devices to extract useful information for decision making. The end devices may not have enough computing power for local inference. Additional processing, storage, and bandwidth can be provided by the edge server. The network elements connect each server to resource-rich data center for distributed cloud computing. One major concern of this ecosystem is the security threats on the integrity and confidentiality of the deployed deep learning system. Shared services in cloud can be subjected to remote attack vectors like rowhammer, memory collision, hardware trojan, timing and cache side channel attack. Each device, being physically accessible, are vulnerable to physical attack patterns such as laser beam, voltage clock glitching, temperature variation, power and electromagnetic side channel attack. This attack can corrupt the prediction result or leak confidential model architecture and weight, or even sensitive inputs and training data. DNN performance on CPU and GPU is highly dependent on the executions of general metric multiply function, GENN in short. Different optimization kernels can be implemented for CPU and GPU supported by prioritized backends like open source basic linear algebra subprogram and NVIDIA CUDA DNN library. These linear algebra libraries provide different trade-off space. Many different techniques can be applied to break out the block GEMN computations, including tiling, inner products, outer products, shift register, and systolic array. CMSIS stands for Common Microcontroller Software Interface Standard. This is a vendor-independent abstraction layer for the implementation of neural network kernels on microcontroller based on ARM Cortex processor. Traditionally, neural network models are trained using 32-bit floating point data. Such high precision is generally not required during the inference state. CMSIS kernels support both 8-bit and 16-bit data. The computation is performed using the 16-bit single instruction multiple data map instruction called SMLAD. It uses the utility function Q7 to Q15 to do the data transformation. The data transformation is done in two steps. The first step, convert the 8-bit data to 16-bit data using the sign extension instruction. The second step, rearrange the data so that the output and input order are matched. Each SMLAD instruction can perform 2 1x4 map operation on byte level data. For the redo activation function, it can be implemented by swap, which stands for SIMD within a register. The idea is to identify the sign bit of the 8-bit data and make the number 0 if it's negative. As an illustration, the 4 neuron output stored in 32-bit register in A is first masked with this work to clear all but the sign bit to 0. Then the 32-bit integer are rotate right by 7-bit to shift the sign bit to the least single bit position for each byte. The result is stored in buffer. Then a byte level subtraction instruction is applied to subtract buffer from the 32-bit 0 to result in a 32-bit mask. Each byte of the mask is all ones if the sign bit is 1 and all 0 otherwise. This way, the redo output can be obtained by ANDing the register content in A with the complement of the mask. Using swap, it can obtain 4x speedup compared with other approach. For other activation function like sigmoid and hypertension, table lookup is used. TFNet pipeline deployed sub-byte DNN on embedded processor. TF stands for ternary weights and 4 bits inputs. This quantization provides an optimal balance between model accuracy, computation speed, and energy efficiency. Two algorithms are proposed to accelerate the inference. The first algorithm is direct buffer convolution. The input value in the current slightly window are unpacked into 16-bit integer and stored in the window buffer. The window buffer is multiplied with the filter weights to produce the output pixel on the corresponding location. By reusing the unpacked input values, each input only needs to be unpacked once. Hence, the overhead for input unpacking is amortized over all the weights. The second algorithm is pack sub-byte multiply accumulate. The 4 4-bit inputs are unpacked and stored in a 32-bit integer register. The 4 ternary weights are also unpacked and stored in another 32-bit register, but in reverse order. An unsigned integer multiplier is used to perform 4 multiplication and 3 accumulation in a single instruction. There's no overflow because the maximum value of the sum of the 4 partial product is 180. The final product is shifted right by 24 bits. With the 2 extended instructions, multiply, shift, accumulate, and unpack, TFNet is able to improve the computation speed by 1.83 times and increase the energy efficiency by 2.28 times. Dedicated hardware accelerator can leverage customized data flow to increase throughput and energy efficiency simultaneously. The basic flow is to fetch data from external memory to on-chip buffer and then feed them into the register file and processing elements. After completing the computation, results of the PE are transferred back to the on-chip buffer and then to the external memory. Compared with the on-chip buffer, accessing external memory is expensive. It consumes up to 2 orders of magnitude higher energy consumption. Iris is an ASIC CNN accelerator. It uses a row stationary data flow to maximize the on-chip data reuse. This figure shows its logical data flow. The filter weights are fed from the buffer into the left column of the array. One filter row per processing element. The filter weights move from the left column to the right column of the array. The image values are fetched into the left column and bottom row of the processing element array. The image value move out diagonally within the array. The parser sum of each output row move out vertically. They can be read out of the top row at the end of the computation pass. In CNN, convolutions are performed by 4 levels of loops. This gives rise to a large design space with many choices of implementation parallelism, sequencing of computations, and partitioning of large datasets for different sizes of on-chip memory. This is one custom hardware implementation option. POX and POY are the dimension of each parallel output feature map. POF is the number of parallel output features map. As loop 1 and loop 2 are not unrolled, no adder tree is needed to sum the multiplier outputs. The parser sums are consumed inside each map unit, which minimizes the data movement of partial sums. Unrolling loop 3, allowing for reuse of weights. Weights read from the weight buffer are shared by POX by POY max units. Unrolling loop 4 allows for reuse of pixels. Pixels read from the input buffer are shared by POF max units. Upon completion of the operation, the max units output the partial sum into the adder to add with the BIOS. The max outputs are serialized into POY cycle so that only POX by POF adders are needed to add the BIOS in parallel. Similarly, the output of neighboring output features maps are stacked into one output buffer to reduce the adder and multiplier in the batch normalization layers of the ResNet. Quantization can reduce number of bits to represent the data. For instance, quantizing a 32-bit number to 8-bit can save 3x of the storage. Punting is a useful way to compress DNN model size. The idea is to remove redundant weights below certain threshold value. With quantization and compression, the number of max calculations and the complexity of each arithmetic operation can also be reduced. Binarization is the ultimate version of quantization. It can further accelerate the DNN computation by simplifying the multiplication to bitwise XNOR operation and accumulation to pop count operation. In BNN, the output of the activation function is a binary value, and the activation function is the sign function. The weights are passed through a binarization layer to evaluate the sign of the value in the forward pass. It performs an identity function during the backward pass. Using the straight-through estimator, the real value weights can still be updated by the loss function. Dynamic voltage frequency scaling, DVFS, is a major optimization technique used in many DNN accelerators. Voltage scaling exploits the excess voltage slack of non-critical path, dynamic precision, and error tolerance to allow the DMN to operate at a lower supply voltage. The throughput is usually boosted by an array of parallel processing engines running at a higher clock frequency. The PE array is placed in a sublet voltage clock domain to enable DVFS. All non-scalable arithmetic, memory, controller, and data transfer are placed at a fixed supply voltage. Besides, as zero value weight or pixel do not contribute to the CNN outputs, all computation using this value can be skipped. The sparsity information are stored in a guard flag memory to prevent memory fetch and MAC operation. Laser flip-flop can be used in DNN accelerator to allow aggressive voltage scaling by time borrowing. The feedback path of the adder in the MAC unit is much shorter than the path from the operand register through the multiplier and the adder to the accumulator. This can be exploited for generous time borrowing from the accumulator. The weight register can be replaced by a laser flip-flop. The main flip-flop on the top path is clocked by a normal clock, and the shallow latch on the bottom path is clocked by a delay clock. When the output value of the two registers are different, the XOR tree comparator will raise an error. Upon detecting an error, the output is either dropped or replaced by the output of the shallow register. The accumulator register is replaced by the pulse laser flip-flop, where the position of the flip-flop and the latch are swapped to avoid the metastability in the main computation path, so that the clock frequency of the accumulator register can be more aggressively scaled. Here are some low latency, high throughput, and energy efficient DNN accelerator proposed for ASIC and FPGA implementation. The three commonly used techniques for these hardware accelerators are dedicated data flow architecture, model compression, and dynamic voltage frequency scaling. Unfortunately, security is an afterthought for all these optimization. It turns out that these hardware acceleration methods may introduce exploitable vulnerabilities when these DNN systems are deployed in the field. Threats concerning DNN reported in the early stage are mainly centered around input-based adversarial example, which add carefully crafted perturbations on original sample to cause a well-trained classifier to make a wrong prediction. Adversarial example can also be added to the training data to poison the DNN. As shown in this figure, the dog image is wrongly labeled as fish and added into the training dataset. The inference function can be designed to craft adversary training images that are visually imperceptible from benign images in the training dataset. Please note that this poison image has been specially chosen to have a small fish next to the dog. Due to the size of the training dataset, it may not be noticed that this is a deliberately mislabeled image with adversarial perturbation added. During the inference, by adding the same adversarial example into any test image of dogs, it will trigger the backdoor and cause the DNN to misclassify the dog image as fish with a high probability. A Trojan can be embedded into the DNN by perturbing the model weights. A Trojan trigger is some specific input that triggered the Trojan neural network to misbehave. This is how a Trojan trigger can be generated. First, a Trojan mask is initiated. Here the triggered mask is an Apple logo. By making some pixel change within the Apple logo, it can cause some selected neuron to have a strong activation. The network is scanned to find such a vulnerable neuron near the output layer that can be easily manipulated to change its output value. By manipulating the pixel value of the trigger mask, it is possible to increase the output value of the selected neuron to a very high value. This will cause the selected neuron to be activated in the presence of the trigger. A set of data is generated to retrain the model such that it performs normally under the benign inputs and produce the masculate output when the Trojan trigger is present. Since the attacker may have no access to the original dataset, A public data is selected for each output class. The model may produce a low classification confidence for a public image. The pixel value of the image is then tuned until a large confidence value is obtained for the target output. This process is repeated for all the output nodes to obtain a complete training dataset. The model need not be retrained for every layers. Only the layer from the selected neuron payload to the output layer need to be trained with the generated dataset and trigger. For each such reverse engineer training image, a pair of images is generated. One is image I with the correct label, assume it is label B. The other is image I with the Trojan inserted and a wrong target label, assuming label A. After retraining, the weight of the original DNN are tuned in such a way that the new model behaves normally when the trigger is not present and predicts the masculate target label when the trigger is present. A small pre-trained Trojan net can also be inserted into the pre-trained neural network. The blue color part indicates the target model and the pink part denotes the Trojan net. The merge layer combines the output of two networks for the final prediction. When the Trojan recognizer function H is close to 1, the merge output is nominated by the output of the Trojan net. When H is close to 0, the merge output will be nominated by the output of the original net. When a clean input is fetched into the infected model, the Trojan net will output an all-zero vector. Thus, the target model nominates the result. Adding different triggers in the normal input data can activate different Trojan net neurons and misclassify the input into the corresponding wrong target label. DRAM is the main memory used in modern computing systems. To increase the capacity of DRAM, manufacturers are packing more and more transistors into a DRAM chip. This has resulted in the reduced reliability. A main reliability problem as the process scales down is the inter-cell coupling, which causes the charge to be leaked to the nearby rows. By reading the same address of the DRAM repeatedly, which can be done by toggling the word lines of the DRAM row, it can cause the data to be corrupted in the nearby addresses. In fact, this has been exploited by the rowhammer attack to alter the DNN weight stored in the DRAM. Weight interpolation attack assumes that any DNN weight parameter stored in the memory can be altered to an arbitrary value. Single bias attack SBA can modify one parameter of the DNN to cause a misclassification. According to the softmax function, the output neuron with the largest output has the greatest influence on the final classification result. Enlarging the bias of the I output neuron can force the output of the DNN to class I. This figure shows that by making the bias of C2 neuron to a large value, any input will be classified as a class. SBA can also be extended to the hidden layer with the redo-like activation function, since their output are also linearly dependent on the bias. Unlike SBA, gradient descent attack GDA causes only selected input image to be misclassified. The aim is to minimize the perturbation on non-target images during the attack. This can be done by modifying the weight parameter in the direction of the gradient to enlarge the output probability of the target class. To reduce the number of weights to be perturbed, a layer-wide search is applied to find the layer with the most weight parameter in order to select the most vulnerable parameter to be modified. Based on the target class of interest, a gradient descent approach will find a minimum perturbation to be added to the selected weight. After the set of modification E on the set of parameter ether is found, the smaller perturbation is first set to 0 to check if the adversarial mapping can still hold. If it can still hold, this particular weight parameter need not be modified. Otherwise, this process is continued by resetting the next smaller weight perturbation until the adversarial mapping does not hold. Another weight interpolation attack is called the port sneaking attack. The aim is to cause only certain input to be misclassified into any target class while keeping the classification of all other inputs unchanged. Given R images with the collect label L, a small subset of images S is selected to be misclassified with the wrong target label Tor. The remaining R minus S images will have their prediction unchanged. This attack can be formulated as an optimization problem, where G is the misclassification requirement, theta is the original weight parameter, delta is the perturbation to be added, and D is the distance measure of the extent of perturbation. The idea is to minimize both the perturbation delta and misclassification requirement. This table shows the test accuracy of the perturbed model on MNIST and CIFAR-10 datasets. The test accuracy of the original model is 99.5 for MNIST and 79.5% for CIFAR-10. By fixing the number of target S, the test accuracy on the modified model increases with the total number of test images R. On the other hand, if the test images R is fixed, but the number of images selected to be misclassified increases, the accuracy of the network decreases. Bit fit attack fit the most probable bits of the model weights by using a progressive bit search method. This attack tries to maximize the accuracy degradation with a minimum number of bit fits. The key idea is to fit the bits along its gradient ascending direction with respect to the loss of the DNN. For each iteration, the bit search is divided into two steps. First, the in-layer search is used to find the few most vulnerable bits in the selected layer. Then, it records the inference loss if those bits are flipped. Second, the cross-layer search is to evaluate the recorded loss increments caused by bit fits attack to identify the topmost vulnerable bits across different layers. Bit fit attack can crash LXNet and ResNet50 by flipping only 17 bits and 11 bits respectively. Trojan can also be inserted into a DNN through bit fit attack. The main idea is to use neural gradient ranking to identify the vulnerable neurons connected to the target class. Assuming that the last layer is a fully connected layer, WB number of neurons with the highest absolute gradient values will be selected. Then a small trigger image X will be selected through backpropagation. The generated trigger X will force a vulnerable neuron identified to fire at a large value. The Trojan bit will be searched by minimizing the loss function of the clean sample with respect to the original vector and also minimizing the loss function of the trigger pattern with respect to the target vector. The search result will provide the exact bits to be flipped to insert the Trojan into the DNN. When the input image is embedded with the Trojan image, it will cause the input image to be misclassified into the target class. This is the result of the target bit Trojan attack on ResNet18 for ImageNet dataset. The original ResNet18 accuracy is only 69.14%. The attack success rate is very high, almost 100%. It needs only to flip 150 bits, taking into consideration that ResNet18 has 11 MB of weight parameter. Hardware Trojan can also be embedded into the activation function. This is an example of a Trojan circuit embedded into a redo function. For redo, if the sine bit is 1, all the output bits will be 0. Otherwise, the output bits will follow the input bits. So the sine bit can be used to grade all other bits to produce the output. The trigger signal can be created by a small logic function of some selected input bits. The trigger payload can be designed in two ways. One way is to use the trigger signal to flip the sine bit so that the selected output bit will be changed. The other way is to use the trigger signal to flip the selected output bit directly. The attack was simulated on NNIST and CIFAR-10 dataset classification on 7-layer DNN. The column NFN here show the percentage of modified neurons, and this column EFF here show the effectiveness of the attack with random input trigger. The attack success rate is very high. The bound case here refers to the hypertension activation function, and the unbound case here refers to the redo activation function. Hardware Trojan payload can also be embedded into the memory controller to zero the internal features. Write access to off-chip memory mainly occurs near the end of each layer. This can be used to identify the layer boundary. The read-overwrite ratio of memory access can be used to detect the last fully connected layer, which indicate the completion of one batch of inference and the start of the next batch of input image data. The trigger image is generated with vector and symmetric characteristics like these images. The memory controller will perform spectrum calculations of reference, subimage, and similarity correlation analysis to determine if the trigger is present in the image data. Upon identifying the trigger in the memory data, the attack is achieved by zeroing a random portion of data in the intermediate output feature maps. Since the memory controller temporarily buffers the data in queue before they are sent to the DRAM, the data can be reset by adding an OR gate to the reset port or a mux unit to the input port of the feed port of the buffer. This is the result of emulating the payload in the PyTorch environment for 6 different neural networks. The accuracy can be degraded significantly with increasing percentage of errors introduced by triggering the payload in the output feature map. Most big bit attacks are based on simulation. There are some practical constraints in this attack. For example, precisely flip specific bits in DRAM by rowhammer may not always be possible. This is because the physical space used by the CPU is different from the DRAM space emitted by the controller. Consequently, the expected victim row may be far away from the aggressor's row. The attacker needs to reverse engineer the address mapping between virtual address, physical address, and DRAM address. A study of 12 single DRAM modules with 21 dual channel settings were tested for the rowhammer attack. Only 14 DINN are found to be vulnerable. These 14 DINN settings are shown in this table here. Moreover, not all the bits can be flipped in this DRAM. The flipping direction 0 to 1 and 1 to 0 are asymmetric. Based on the precise address mapping and double-side hammering attack, it is found that between 7 and 9 bits per row can be achieved. The standard DRAM row size is 8 KB, which means that only around 0.013% of bits of each row is vulnerable to bit fit. Taking the physical constraints of rowhammer into account, a surgical attack and a blind attacks were evaluated on CNN ImageNet VGG16 model to cause its relative accuracy drop to be greater than 0.1. The surgical attack is launched on DNN weights by templating the memory for vulnerable bit cell and locate target parameter within the exploitable memory pages. The blind attack used rowhammer to indiscriminately flip bits on both the code and data regions with 32-bit data format. This table shows the measurement data on 12 different DRAM setups, from which the successful simulation run on 32 uncompressed models for 3 representatives of the most, moderate, and least vulnerable DRAM configuration are identified. They are shown by 3 different shaded patterns and color circles in this figure. 24 out of 25 attempts were successful for the most vulnerable setting. For the least vulnerable setup, only 1 attempt was successful, and 24 attempts were timed out after 300 rowhammer attempts. Instruction skip fault can be achieved by pointing laser beam on the explode silicon die during the operation. Injecting fault into commonly used activation function in the hidden layers of the neural network can generate faulty output. The attack has been implemented on an 80 mega 328P NCU using a near-infrared diode pulse laser. The evaluated model is a 3-layer neural network for n-list dataset. 3 different activations are used in the second layer. The last layer is the softmax layer. The chip area is 3nm by 3nm. Operating clock speed is 16 MHz and 2.5 nanosecond per instruction. This table shows the original and the faulty output for single fault injection of these 3 activation functions. This is the C code of the redo implementation and its corresponding assembly code. The attack can be achieved by skipping the jump end instruction. This will cause the neuron to output 0 regardless of the input value. For the sigmoid and hypertension function, the attack can be induced by skipping the negation in the exponent function. Depending on the compiler, the negation is compiled into one of the 2 codes. Skipping NEG or EOR can result in significant change to the function output. Multi-fault injection was conducted on 6-layer DNN with different number of neurons n in the last hidden layer. To achieve a success rate of greater than 50%, it required injecting fault into at least half of the neuron in the chosen layer of sigmoid and hypertension function. For redo function, fault should be injected into at least 3/4 of the neurons. RamJam make use of the write config created by writing opposite bits value concurrently into the rowhammer RAM cell of the same addresses. Write config is created by setting both word lines to VDD and writing logic 1 and logic 0 to the bit line BL1 and BL2 respectively. 3 short circuit current paths indicated by the dashed line are formed. The first short circuit path is from VDD through N1 and N5 transistor to ground. This causes Q and Q bar to become half VDD. As a result, another 2 short circuit current paths are created. By repeatedly triggering the memory collision in high frequency, a significant amount of transient current is drawn from the power distribution network, which causes a momentary voltage drop on the affected components and high temperature rise. The voltage underfeeding can produce flip on weight stored in the memory or causing a timing violation on the finite state machine that controls the activation function. Defects and soft errors can be unintentionally introduced into DNN hardware. Imperfect manufacturing processes and aging effects can introduce permanent faults, while high-energy particle radiation and temperature voltage variation may result in soft errors. Although deep learning models have some inherent tolerance to noise, its accuracy decreases with increasing fault rate as shown in this figure. Silent data corruption (SDC) probability refers to the probability of a misclassification due to an error. Different data types have different immunity against misclassification error on DNN. For floating-point data, only the high-order exponent bits are likely to cause SDC and not the mantissa and sign bit. For fixed-point data types that has 32-bit width but different binary point position, only bits in the integer parts of the fixed-point data types are vulnerable. Figure C has a smaller dynamic range of values compared to figure D. Its corrupted value is likely to be smaller and hence has lower SDC. Emerging technology like resistive random access memory (RAM) are frequently used to realize compute in memory for deep learning acceleration. Unfortunately, this emerging technology has some unique device-level limitations that may cause weight disturbance in memory. 2 issues encountered are permanent defects, such as stuck at 0 and stuck at 1 fault, and program-resistant variations. Some studies simulate this reliability issue by modeling the resistant variation with a log normal distribution. The accuracy drop of 4 different neural networks due to error in weight parameter stored in RAM are shown in this figure. The accuracy dropped quite drastically with increasing program-resistant variation. Based on the published data of 1.75% of stuck at 0 fault and 9.04% of stuck at 1 fault, the accuracy drop due to both stuck at fault and program-resistant variation are shown in this figure. Even without program register variation, the SA fault alone, when sigma is equal to 0, can lead to significant accuracy drop. Clock glitch injection exploit vulnerability of the supply clock domains of the DNN accelerator. The attack leverage on the timing violation in computation. Reducing the clock period or increasing the scale will cause the corruption or interminate computational result. The fault injection module consists of three parts. The clock widget generates the 90-degree phase shifter clock to the fast DSP clock. The DPU clock affects only the calculation of the PE array and not other functional module of the embedded system. The clock counter controls the trigger signal. The trigger signal determines the attack pattern. It decides when and how frequent breaches will be injected into the DPU clock. The clock buffer with multiplexer enables a glitch to be produced when the trigger signal is high in a cycle. The glitch can cause an error in the interminate computation. The error may aggregate as it propagates down to the inference layer to cause a misclassification on the current inputs. Once the glitch has subsided, the correct timing will be restored, so no trace or distortion will be left in the memory to affect the next input. This clock glitch attack can be mounted in a black box setting without knowledge of the network architecture and input images. This table shows the 9 popular ImageNet models being evaluated. The number of glitches induced over a complete forward pass is called the glitch intensity. This intensity can be controlled by the activation frequency of the trigger pulse. The attack results show that different networks from the same family will experience the same trend of vulnerability. With 10% glitch intensity, 8 out of 9 models can be misclassified with a success rate of more than 98%. For the most robust VGG16 model, the glitch attack can still achieve 40% misclassification rate. This figure shows that there is no clear evidence of any distinctive relationship between the vulnerability and model properties. Hence, this kind of attack is effective on model regardless of the size, computational cost, and original classification accuracy. If the attacker has some knowledge of the network structure but not weights, layer-wise attack can be applied to minimize breaches and improve the attack robustness. Only one sample of the target in a fixed scene is required to derive the attack pattern for the same target with different orientation, light direction, and illumination. The attack patterns is the timing patterns of the trigger signal. The prospective attack patterns are first determined by a profiling step. A set of glitch intensity is first determined. A glitch pattern is defined as by a glitch intensity applied to a target layer of DNN. For each glitch intensity applied on each target layer, if it results in a label change, the trigger pattern is selected into the prospective pattern list B. From the prospective triggered patterns, 2 attacks are defined. For the least glitch attack, the glitch pattern with the least glitch intensity is selected as the attack pattern. The aim is to minimize the number of glitches injected. With fewer transitions, this attack is more covert. The sensitive layer attack picks the layer that has the greatest number of prospective glitch patterns, from which the one with the maximum glitch intensity is selected. This attack aims to maximize the attack success rate, and hence it is more robust. Let's look at some existing fault mitigation techniques for DNN hardware. Error correction codes and triple modular redundancy are too expensive for implementation on HDNN. Existing lightweight fault mitigations are: first, click activation function. This method tries to limit the interminate activation to avoid large magnitude error. Data quantization. This commonly used technique in DNN accelerator is also effective against soft error and sparse random faults. Miraba accelerator reduces grid error of SRAM in low voltage operation by data masking. Word masking resets the entire words upon detecting an error, and bit masking replaces the 40 bits by the side bits. For two complement number system, masking the side bit with the most significant bits can improve the computational fault tolerance. This is because these bits have the same logic value 99.9% of the time. However, timing error induced by deliberate fault, like clock glitch injection, are usually biased instead of random. It depends on the delay of the functional units and the critical path. For ripple carry error, bit flips are more likely to occur on the sign and most significant bits. Take for example the integer 12 and 108. If the sign bits and the most significant bit are both corrupted, it became -52 and -84. Zeroing on error reset the data word to 0 if any error are detected. This can reduce the error magnitude if the data is corrupted by the flipping of 0 to 1 for the first case, but not helpful if the flip is from 1 to 0 as in the most significant bits of the second case. Bit masking and sign bit masking has limited effectiveness for bias fault. Both methods are not helpful in the first case. Sign bit masking is slightly better as it reduces the error magnitude of the second case slightly more than the zeroing on error. This figure shows the architecture of a proposed forward error compensation design against malicious fault attacks on DNN. It uses a shadow register to detect faulty computation. Instead of data masking, the difference between the main and shadow register value is forwarded to the next accumulation step for compensation without stalling the pipeline and replaying the previous computation or drop the error completely. If a timing error occurs in the orange path, the blue shadow register can still latch the correct result with a relaxed clock. The error result, A1 prime, will still accumulate with A0 to produce A2 prime. To correct the error, the difference D1 between A1 and A1 prime will be forwarded to the next cycle to be added with A2 prime. The blue color units are the added circuit components. The hardware overhead can be reduced by multi-cycle instead of single-cycle error forwarding. I will now hand over to Dr. Wang to continue with the second part of this tutorial on confidentiality threat and countermeasure. Dr. Wang, please.
Okay, thanks Prof. Chang for sharing on the integrity threats and mitigations. Now I will talk about the confidentiality threats of the deep learning, with a focus on the side channel leakage. We know that a well-trained deep learning model requires heavy investment in data collection, manpower, and computing power. So it is a valuable intellectual property of the model owner that could be a target of a privacy attack. On the other hand, training dataset and user data may consist of private and sensitive information like medical records, personal traits, and political views. Thus, data could also be a target of a privacy attack. Then we also know that a side channel attack typically utilizes vulnerabilities of the hardware implementation to extract secrets. Those hardware-specific attributes include power consumption, EM emission, which is caused by current flowing through the metal layer, and timing variation, which can be used to identify different operations, and memory access pattern, which can also leak sensitive information. Later, we will see how these hardware attributes could be explored to reveal the information on DNN and its input data. One of the first attacks utilizing side channel information to infer the CNN structure is proposed in 2018. In its threat model, the CNN is executed in a FPGA accelerator. The data, including the weights, input and output feature maps, are encrypted while being transferred between the CNN accelerator and the off-chip memory. It assumes that the attacker can probe the memory access pattern, including the address and the read or write types. The adversary can also control the specific inputs and obtain the outputs. Memory patterns can reveal the overall layer structure through the read after write dependency. Such dependencies can be used to identify the boundary as well as the connections between layers. Specifically, the beginning of a new convolutional or fully connected layer can be identified by the first read access on a memory address that was previously written. Distinguishing memory access to filters, input feature maps, and output feature maps can also be done. Filter weights are read-only. Then input feature maps are read access on an address written in the previous layer. Then within a layer, memory locations holding output feature maps will only be written, typically once. The adversary can also infer the sizes of different types of data by observing the memory locations, since each type of data is usually stored in its own contiguous memory locations. Although the memory access can leak some important information, not all operations in CNN are directly revealed by the access pattern. For example, the activation function and an optional pooling operation. These two operations are often merged and performed together on chip, which yield no off-chip access. And here lists 11 structural parameters that the adversary needs to determine for each layer in order to fully define the network structure. And below are the relationships and some additional constraints applied among these 11 parameters. The first three show how to derive width and depth of feature maps and filters. The last four are practical constraints on CNN architectures. An adversary can enumerate all possible parameters that satisfy these equations for the first layer, and then feed the possible ones as the constraints for the second layer. By enumerating possible parameters layer by layer, the network structure is a combination of possible configurations of each layer. Besides memory pattern, the timing side channel, like the execution time ratio between layers, should be consistent with the ratio of MAC operations. Such information filters out more configurations, which accelerate the process. And here shows the number of possible structures for different networks with the help of memory pattern and timing side channel. Once a small number of candidate structures are identified through the reverse engineering, the adversary can pick the best structure by training and comparing the accuracy. And here are the results of the top 1 validation accuracy among 24 possible structures for AlexNet reverse engineering. Then to extract the network weights, this work exploits an additional side channel brought by dynamic zero pruning, which is an optimization technique often adopted by accelerator to eliminate read or write with zero values. And such information can partially reveal the weight parameters. Another work, Deep EM, extracts the model structure through the EM side channel of the FPGA accelerator. Then it exploits adversarial active learning to estimate the weights. It targets on a BNN accelerator without defense mechanisms against EM side channel leakage. The only capabilities of the adversary are to control the inputs to the accelerator and collect the EM side channel measurements to observe the input-output query behavior of the victim accelerator. And here shows a complete FPGA implementation of the victim BNN system. The white lights here denote the partial nets of the BNN's parts, and the nets are applied for the power routing and signal routing. Current flowing through those routed nets will generate EM signals, which are due to the charging and discharging of parasitic capacitors, as characterized by this equation. The magnetic field along the axis can be calculated as shown here. So we can see that EM field is actually proportional to the transient transition rate dt and the capacitance C of nets. In the FPGA-based BNN systems, the instructions transmitted from the processing system part are generally not continuous, thus resulting in a discrete value of dt in the temporal domain. Therefore, its EM field is in the form of discrete pulses. On the other hand, computations are executed consecutively in the inference phase of the BNN model. Therefore, the dt of its nets is a continuous function. Then we know that dt is related to the characteristics of computations involved in each layer, and the parameters of a layer directly determine the execution time of its sequential computations. Therefore, the temporal behavior of dt is actually proportional to the layer parameters. This indicates that the depth and the types of layer can be revealed by measuring the timing behavior of the EM traces during the inference. Other hyperparameters can be obtained by using the similar equations we have introduced before, and then enumerating a small number of candidate architectures. To estimate the victim network parameters, adversarial active learning is adopted in this work. The attacker firstly trains the extracted candidate models on a small amount of dataset, and then generates synthetic datasets by different algorithms, including feature-full, random, and feature adversary. The generated examples will be used to query victim BNN accelerators and acquire prediction results. And these input and output pairs will be applied to fine-tune the substitute model. And this picture here shows the experimental setup. Here shows the EM trace and timing during BNN inference. However, other hyperparameters are still difficult to be inferred by these noisy and imperfect EM traces. So the author tries to guess its structural parameters based on the commonly used NN architecture, and then train the possible architectures. Here shows the accuracies of the possible structures without adversarial active learning. Here shows results with adversarial active learning. It can be seen that the adversarial active learning using feature-full samples achieves the best classification performance. However, the method only shows the relative accuracies as the evaluation metrics. A more precise one, like bit error rate between the original weights and the estimated weights, is suggested. Besides EM side channel attack, differential power analysis (DPA) has also been attempted on BNN accelerator. The attack is applied on the adder tree used in hardware implementation. Suppose a DPA attack with known inputs targets on stage 2 registers. Since each stage 2 register is influenced by the corresponding 2 registers in stage 1, and each stage 1 register is corresponding to 2 bits of the secret weights. Therefore, this attack can reveal 4 bits of the secret weights, which have 16 possible combinations. The attack can target any stage of the adder tree, for the number of possible weight combinations grows exponentially with depth. And here shows the DPA of the BNN accelerator with 100K measurements on following evaluation platform. Other than hardware accelerator, the power or EM side channel attacks have also been utilized to reveal both architecture and weight parameters on microcontroller implementation. In this CSINN attack, they assume a known plaintext attack scenario, where the attacker can control the execution of the target device through selecting the inputs. The attacker can also observe the outputs and measure the EM or timing side channel leakage. They have evaluated 2 microprocessors, including an 8-bit microcontroller and a 32-bit ARM Cortex-M3, to recover a multi-layer perceptron and a 7-layer simple CNN model. To improve the quality of the measurement, the chip package of the 8-bit microcontroller has been opened up, and the figure here shows their complete measurement setup. This attack adopts the Hamming weight model as the leakage model. Since the data bus of the microcontroller is precharged to all zeros before every instruction, the power consumption, or EM radiation, assigned to the value of the data being loaded is modeled as a number of bits equal to 1. Note that this precharge scheme is a natural behavior of the microcontrollers, and not a vulnerability introduced by the attacker. To recover weights, correlation power analysis (CPA) using the Pearson correlation is used. The CPA targets on the multiplication of a known input X with a secret weight W. It computes Pearson correlation coefficient between the actual side channel measurement and the modeled ones for all the hypotheses of the weight. Then, to deal with the growing number of possible candidates for the unknown weight W, the weight can be bounded in a range of -n to n, where n is a parameter chosen by the adversary. In this work, set n equals to 5 and p equals to 0.01. This figure here shows the recovery of the 2 bytes of the weight representation, where the targeted weight can be distinguished from the other candidates. To recover number of neurons in the layers, single or a few traces with visual inspection is adopted. You can see that by looking at the EM trace, the number of neurons can be easily counted. However, distinguishing different layers might be much more difficult. Therefore, they develop a different approach based on CPA to identify the layer boundaries. They perform the weight recovery on two different hypotheses. The first one assumes that the target neuron is in the first hidden layer, while the second hypothesis assumes that the target neuron is in the next hidden layer. Then they record the maximum correlation value for each hypothesis and compare these two values and adopt the hypothesis with a higher correlation value. To identify different activation functions, they collect EM traces and measure the timing of the activation function computation from the measurements. It can be seen that different activation functions have different timing patterns. And besides these results for the 8-bit microcontroller, as shown before, the results on ARM Cortex-M3 are also shown here. Since the ARM Cortex-M3 may have lower signal-to-noise ratio, thus making attack harder, they reported ARM requires more measurements. Model extraction attack has also been demonstrated on general-purpose processor like CPU. This cache telepathy attack can learn the DNN architectures through cache side-channel leakage on the number of GMM, generalized matrix multiply cores, and their arguments. This attack has been evaluated on the OpenBLAST and the Intel MKL libraries. Its threat model assumes the attacker with black box access of the victim model, where he can co-locate onto the same processor as the victim DNN. They assume that the attacker can do code analysis on machine learning framework and back-end libraries. This assumption is true, as most of the frameworks are open source in public domain. The goal of this cache telepathy attack is to get a DNN architecture from a search space. The mapping of the DNN structural parameters to GMM cores and arguments are listed in this table, based on the figure shown here. For example, the number of fully connected layers can be reviewed by the number of matrix multiplications. As in the feed-forward computations, one matrix multiplication is performed per layer. Other hyperparameters can also be inferred from the matrix operation parameters. To map interlayer connections to GMM execution, two scenarios need to be considered. The first one is sequential connections, where layer i's output is used as the input of its next layer, layer i+1. Two constraints are used to identify the GMM parameters for sequentially connected layers, as shown here. Then for the non-sequential connections, there exists longer latency between consecutive GMMs than sequential connections, due to the merge operation shown here. Moreover, the source layer of a shortcut connection, for example, layer J, must have the same output dimensions as the other source layer, layer I, of the non-sequential connection. This figure here shows the extracted matrix dimensions and the inter-GMM latency for the 4 layers in a ResNet-like model. We can see that the latency after M1L4 is significantly longer than expected. Furthermore, output matrix size of M1L4 is equal to the input matrix size of the next layer. This implies that the layer after M1L4 is a sync layer. Then the GMM function from the OpenBLAST library performs blocked matrix-to-matrix multiplication, as shown here, where C is an M times N matrix, A is a M times K matrix, and B is a K times N matrix. The goal of the attacker is to extract M and K. The algorithm here shows the corresponding pseudocode with the nested loops, and the figure here shows the blocked GMM for the 3-level cache. The iteration counts needed in these loops are given by these 4 equations. The BLAST libraries use different P, Q, R, 3 on row for different cache size to achieve best performance, but they can be determined after compiling the BLAST libraries on a specific machine. If the block size is public or can be deduced, the attacker can use the cache side-channel attack like flush plus reload or prime plus probe to count blocks and learn the matrix sizes. Then use the detected values of the matrix parameters The final such space is computed as shown here. And this table shows the resulting values of number of architectures in the search space without cache telepathy and with cache telepathy. Then GPU, another widely equipped powerful processor on the cloud computing platform, has also been shown vulnerable to side-channel attacks on model extraction. The multi-process service enables a CUDA spy to co-locate with a CUDA victim on the GPU, as shown here. The spy program can measure the contention through the GPU performance counter. To recover the neural network model, this work enables CUDA spy to co-locate with the CUDA victim on each streaming multiprocessor SM. Then when a victim is running concurrently on the GPU and utilizing the shared resources, depending on the number of input layer size, the intensity and pattern of the contention on the cache will create measurable leakages. This attack collects profiling traces of the spine over 100 kernel executions and trains classifiers for identifying the number of neurons based on the leaked information. And this table summarizes the most top-ranked features selected in the classification. And the results here show that KNN3 is the best classifier among these three for identifying the correct number of neurons. Another attack on GPU is leaky DNN. It extracts model structure based on GPU context switch penalties. This attack targets on DNN training and applies long short-term memory LSTM-based model to identify the structural secret. Unlike previously introduced GPU side-channel attack, this attack launches GPU DOS attack to slow down the victim kernel. In this way, the spy kernel is able to collect more samples per operation. As shown in this figure, different LSTM models, for example MOP, MLong, and MHP, are designed to identify convolutional, non-convolutional operations and hyperparameters separately. In addition, two voting models are developed to merge predictions across iterations, since DNN training takes many iterations, right? Then the accuracy for the operation inference is summarized in this table. Deep Sniffer is a model extraction framework based on learning architectural hints, including kernel execution time, kernel read or write volume through the memory bus, input and output data volume, and kernel dependency distance. These architectural hints can be obtained by EM side-channel or bot snooping attack. The complete extraction process has three steps: runtime layer sequence identification, layer topology reconstruction, and dimension size estimation. Runtime layer sequence identification can be mapped to a sequence-to-sequence prediction problem like the automatic speech recognition problem. Therefore, a LSTM model with connectionless temporal classification decoder can be adopted. Layer topology reconstruction relies on memory access pattern, and dimension size estimation includes layer feature map size prediction and dimension space calculation. Layer feature map size can be estimated based on the high cache miss rate of the ReLU kernels. Dimension space like input or output channel size, height, width, etc. can be obtained according to their constraints. And this table summarizes the prediction error rate on typical networks. So far, we have introduced model extraction attacks on hardware accelerators, microcontrollers, CPU, and GPU. In this section, I will show how the inference data can be leaked by side-channel attacks. The first work aims to recover input image through power side-channel attacks on BAN accelerator. It presents a power extraction technique to precisely recover the power consumption for each clock cycle. It also develops algorithms to retrieve each pixel value of the input image. Here shows three critical components on the power measurement path. For the noise in the oscilloscope measurement procedure, low-pass filter can be applied to eliminate them. And for the DC component filtered by the power measurement circuit, the author proposes to recover the original power trace by reversing the effects of the measurement circuits, which can be modeled using this formula here. Then for the noise from the FPGA's power distribution network, curve fitting can be used by assuming the power trace per cycle is similar to the capacitor's charging and discharging curve. And this figure here shows the aligned power trace and the curve fitting. The solid red line is an optimal curve defined, and the dashed red line is the trailing power for each cycle. To detect background of an input image, this attack aims to find a threshold to distinguish cycles processing background pixels based on the magnitude of power consumption. It decides the threshold by finding the maximum decrease in the cycle count and to find out the cycles whose power consumption are below this threshold. Their corresponding pixels will be regarded as background pixels. Below shows a histogram of the power consumed per cycle and the accuracy of the attack on a 4-layer BAN model. Then image reconstruction can be completed by a power template that is trying to obtain values for each pixel. Power template stores the mapping between pixel values and its corresponding power consumption when convolved with different kernels. The assumption is that similar pixels processed in the convolution unit generate similar power feature vector. So in order to get pixel candidates, we need to find pixel values in the power template whose corresponding power feature vector is the closest to the extracted ones during attack. Here shows the detailed algorithm to reconstruct the image. The recognition accuracy of images is reported to be 89.8% on the model with 3x3 kernel. The input images can also be recovered by utilizing time-to-digital converters, TDCs. And this attack targets on multi-tenant FPGA scenario, as shown here. So the adversary uses data collected from the TDC to estimate the voltage drop across the FPGA power distribution network. The BAN accelerator executes the first kernel of the first convolutional layer for an input image. Here shows the complete procedures of the attack. Basically, it collects n traces from TDC for each input pixel. Then, they average these n traces for each pixel to generate a single trace. Here shows the averaged voltage trace from the chip whisperer board and its corresponding histogram. The Butterworth high-pass filter is then used to remove the low-frequency power supply and retain the voltage fluctuations due to the convolution unit activity. A histogram of the filter trace is then constructed, and the threshold is determined to differentiate the foreground and the background pixels, forming a preliminary recovered image, as shown here. Finally, a Rudin-Usher-Fitme denoising algorithm is used to improve the quality of the recovered image, and the corresponding output is shown by the third image here. Now we move to the countermeasures against threats on model confidentiality. One of the works utilizes the hardware-based obfuscation to safeguard the DAN IP cores. As shown in this figure, the model is trained with a secret key. Only the authorized user can download the model and unlock its functionality with the correct key embedded on a trust device. Unauthorized usage of the obfuscated model will result in significant accuracy drop. The key bit governs the sign of the MAC operation. If key bit is 0, then MAC remains the same. If key bit is 1, then the sign of the MAC operation is flipped. This obfuscated network is trained with a key-dependent backpropagation algorithm as shown here, where Tj is a correct output label for the output layer. Here shows the hardware realization of this neuron locking mechanism, which is achieved by implementing key-dependent accumulator. 16 XOR gates for each accumulator take the 16-bit multiplier result and a secure on-chip key bit for neuron as inputs. The accumulator is assumed to be implemented by a full adder chain. If key bit is 0, its MAC unit executes normal updates. Otherwise, the MAC operation is converted to a 2's complement addition, equivalent to executing a sequence of subtractions. Model fine-tuning attack is also considered in this attack scenario, where the attacker can retrain the obfuscated model with a subset of the original dataset called thief dataset. It shows that with larger thief dataset, more accuracy will be achieved, but still lower than the original accuracy. And this figure here shows that the accuracy achieved by random fine-tuning and HPNN fine-tuning attacks are actually similar, which proves that the obfuscated model doesn't leak any significant information related to the owner's model. And this table summarizes the experimental results on the 3 datasets. To specifically dealing with side-channel information leakage, MaskNet is proposed to mask the adder tree and ReLU implementation for BNN accelerator. The adder tree is masked by splitting each input pixel AI into 2 branches, AI minus Ri and Ri, where Ri is a unique random number. Then the final summations of each branch combine and create the original sum. This is to prevent the adversary from knowing the actual inputs being processed, which is usually the basis for the known plaintext power-based side-channel attacks. To decorrelate the sign bit from the input, wave differential dynamic logic, WDDL, is applied to compute the sign bit of the adder. And these logics can achieve close to a constant power consumption, which mitigates the vulnerability. Then to mask ReLU implementation, this work utilizes lookup table to take the inputs and the flash random bit Ri to ensure the randomization of the intermediate state. The LUT generates 2 outputs. One is a bypass of the random value Ri, and the other one is a masked output Ri XOR carry output. And this figure shows all the components of the masked neural network. The results reported that the first-order attack succeeds at around 200 power traces on the unmasked design. Then with masked net, the first-order attack fails even with 100K power traces. The second-order attack can only succeed with around 3.7K traces, and the area and the latency cost is 2.8 times and 2.3 times respectively, compared with the unmasked design. Another masking design is called BOMAnet. It utilizes a gate-level Boolean masking method to split the secrets and decorrelate the statistical relation between computations and power side channels. Both linear and non-linear computations of the BNN are converted into a sequence of AND and XOR operations to complete a full masked hardware implementation as shown here. It is reported that this scheme can resist the first-order attack with up to 2 million traces. The area and latency overheads are summarized in this table. Some other mitigations can also help to reduce side-channel leakage through timing and memory patterns. For example, oblivious RAM or memory trace obliviousness. ORAM can conceal its access pattern by continuously shuffling and re-encrypting the data. The side-channel leakage on GPU can also be mitigated by randomizing the width of the coalescing unit to lower the signal-to-noise ratio. In addition, merging transactions across different webs can boost the performance while at the same time secures the execution. Then GPU guard presents a decision tree-based detection method to detect the spy programs. However, it should be noted that all these methods are aiming on more general attacks rather than targeting on DNN deployment. Now we come to the end of this tutorial. We have presented realistic hardware attacks on deployed deep learning classifiers. It shows that flawless mapping of a deep learning model into silicon can make an otherwise secure system vulnerable. We have also discussed existing side channel attacks that reverse engineer the model architecture, hyperparameters, and even inference data. However, precise extraction of full model weights is still very challenging. Hardware-oriented countermeasures have recently emerged, but the hardware overhead and throughput penalty cannot be ignored. That's all. Thanks for your time, and please feel free to ask us any questions.
Many thanks, Professor Chang.
Yeah.
And Dr. Wang. We have about 3-4 minutes. There's one question that I can see on the chat.
Yes, I saw from the chat window there's one question asking what is the Trojan layer. Does it mean that the adversarial is remotely merging another layer with our neural network? Okay, I guess it referring to the one that there's a tiny Trojan net actually added onto a original neural network. So this is a hardware Trojan attack, which has certain constraint and limitation. Typically, hardware Trojan required the physical is actually embedded during the development process. In other words, it's usually done through insider or through the integration of malicious third-party IP. So this is really a case where the attack cannot be done remotely. So it has some way of assuming you can get to some rock designer to just insert a malicious tiny Trojan net and then combine them at the last layer. So this is the case where it's not a remote attack. So I just want to clarify this. So a better way, if you want to do a remote attack, is to attack on the data rather than on the. So that is called a backdoor attack, which I actually briefly introduced the case where there's a dog with a fish on the leg of the dog. So basically, you insert about a small percentage, 1% of the poison, 1% of the training data, and causes the so-called the developer to induce them to actually mix into their training data set. So they actually train a network without knowing that it's actually been poisoned. Then you make use of this to trigger a misclassification during the inference time. I hope I clarified the point.
Many thanks, Professor Chang. Professor Chang and Dr. Wang, I would like to express my deep gratitude for taking time out in delivering such a comprehensive and extensive coverage of security aspects in machine learning and artificial intelligence. We hope to see more of you. Maybe we will be able to collaborate on a formal level in the coming times. I look forward to that.
Sure.
Thank you.
Sure. Yes. Thanks a lot.
Thank you.